Welcome to another lecture on quantum computing. We have seen a hint in our lectures that Fourier analysis plays a big role in quantum computing in the sense that there are groups for which we can perform Fourier analysis on the groups and come up with algorithms for natural computational problems. We will see such algorithms as Simon's algorithms and Shor's algorithms in the course, but today our discussion is going to be completely classical. We will see what does it mean to do Fourier analysis on an abelian group. So then I will briefly introduce groups and characters and then talk about Fourier analysis. Let's start with the basics, just to remind you about the things, and then we will move to Fourier analysis. So what is a group? A group is basically a set and an operation, right? And then if you remember, there are properties like it should be closed, under operation, it should have inverses, it should have an identity. But I assume that you are already familiar with the groups. What we need to remember is that this is a set with slightly more structure. It's not just some collection of unordered elements. It has another operation and the elements inside the set behave well under these operations. What does it mean well? That means if you take two elements of the set, you apply the operation, you still remain under the set. For there exists an identity, that means there is this special element E such that G plus E is equal to E plus G is equal to G. This is called identity. And then we have inverses, that means there always exists a G inverse for all G such that G plus G inverse is equal to identity. Great. So since you are already familiar, let's move ahead. There are many examples, complex numbers, reals, integers. These are all groups under addition, and many of them without zero will also be groups under multiplication. But anyway, our story today is about finite groups, so let's take the simplest group in some sense. The simplest group is just probably number 1 or number 0, just an identity. But what I mean is the simplest non-trivial group. I would say that the simplest non-trivial group is Z2. This is a group with two elements where the operation is addition, right? So that means 0 plus 0 equal to 0, 1 plus 0 equal to 1, and 1 plus 1 is equal to 0. You can also call it the group of two elements where the operation is addition modulo 2. And you see that if you take two elements, add them, you always remain inside the group. There is an identity, and for every element there is an inverse. This is a very simple setting. We are going to be almost there, but we will see two extensions of this simple group Z2. We can say, why not take more than two elements? Let's take k elements and talk about addition modulo k. This would be called the group Zk. This will have elements 0, 1, 2 up to k minus 1. You can think of them as congruence classes also, but simply put, there are k elements here and you take addition modulo k, then you always remain inside this set, and this is also a very simple group. Specifically, we can talk about Z to the power k, where the number of elements is a power of 2. And I would like to distinguish this group with another group which is Z to the power k. because these two groups will feature integrally in this course on quantum computing. So we have group Z 2 to the power k. This is a set with 2 to the power k elements where operation is addition modulo 2 to the power k. This is also a group which has 2 to the power k elements, but the operation is going to be different. So let's see what is this group. To take the simplest example, Z2 square, now we are going to have two coordinates. So the elements are going to be 0, 0, 0, 1, 1, 0, 1, 1. And then the operation is addition modulo 2 coordinate wise. I'm talking about simple as in English. I'm assuming people have bare knowledge of group theory, so I'm not talking about mathematical simple, algebra simple. When I say simplest, I mean in English, like the easiest to conceive kind of a thing. Thank you. Yes, so this group is, even though the number of elements are the same and the notation is also similar, but they are very, very different because the operation is very different. Z2 to the square or Z2 to the power k is going to have k coordinates, and we are going to have addition modulo 2 as the operation on each coordinate. What it means is, suppose I want to apply group operation on these two. I will take this coordinate, apply addition modulo 2, which is 1. Then I'm going to take this coordinate, apply addition modulo 2. This is 1, 0. Okay, so this way I can do addition modulo 2 coordinate wise. And a very easy way to remember the difference between these two groups is by remembering that in this group, every element has order 2. What it means is that if G is Z2 to the power K, then G plus G is equal to identity, which we denote by 0, 0, 0, 0. And this is definitely not true for Z2 to the power K. For example, if I take the elements are 0, 1 up to 2 to the power K minus 1, and if I take element 1, 1 plus 1 is 2, which is not 0, which is not the identity. So even though these groups have similar names and same size, they are very, very different in terms of group structure. And when we are here, we will represent the elements as string of length k, binary strings of length k, and here we will represent them by numbers 0, 1 to the power k minus 1. Though both groups will be important for us when we design Fourier transform, when we design quantum algorithms on it. And once we talk about groups, another important concept is subgroup. So H is a subgroup of G if, as a set, H is a subset of G and H satisfies the properties of groups. The way to say this is that it's a group in itself. So that would be a subgroup. So two things, it should be a subset in the definition of a set, and it should be a group in itself. Then it is called a subgroup. And just to make you more familiar with this, let's find out different subgroups of Z2 to the power k. Correct? Then there is a trivial subgroup. What is the trivial subgroup of Z to the power k? Just the element identity. Which is 0, 0, 0 in our case. It is very clear that it is a subset. Also, this has just one element which is identity, which is its own inverse, and it is closed under everything. So then it's a subgroup itself. But then let's take simplest non-trivial subgroup, and again simplest as in English, and the simplest non-trivial subgroup, we will say that, let's say that we have one element 0, 0, 0, and let's take another of your favorite element, okay, which is not 0, 0, 0. So let's say this is my element in the group, and now since I know that this subset, if it has to form a subgroup, it has to be closed under addition. So let's start adding them. Let's call it G1, let's call it G2. So G1 plus G1, 0, 0, 0 plus 0, 0, 0 is again G1. And since this is Z2 to the power k, every element is order 2, that means G2 plus G2 is identity, or G1. That means we don't have to add any more element to find a subgroup. This is already a subgroup of our big group Z2 to the power.
It might be implicit, but the subgroup should have the same operation.
Yes, thank you. So this I should make sense to say that, I should clarify this. It satisfies the properties of group in the sense that it has the same operation as G. Thanks for this clarification. Great, and this should look familiar to you because in Simon's algorithm, when we color the vertices, all the coloring pairs, all the pairs which are the same colors look like this or copies of this in certain sense. And we will talk about this very soon, but let's look at, let's say, biggest subgroup of Z2 to the power k. And again, trivially Z2 to the power k is a subgroup of Z2 to the power k, but move on. What are non-trivial subgroups of Z2 to the power k? And if you have studied group theory, you would have seen that the cardinality of H actually divides cardinality of G, and since cardinality of G is to the power k, we have a non-trivial subgroup. That means the biggest cardinality of H is going to be to the power k minus 1. And in this case, what is going to happen is that your group will be divided into two parts. One is H, and let's say there is an element which is not in H but part of G. then the second part here is going to look like G plus H. What it means is that this part is, so this is almost a copy of GH, but with every element of H we add G, and this is called a coset of G for subgroup H. And we also know that size of H is same as size of G plus H. And this should remind you of the setting of either Deutsch-Jozsa or Bernstein-Vazirani. Actually, in Deutsch-Jozsa, the two groups need not be subgroups, but in the case of Bernstein-Vazirani, we have a function on G or a function on Z2 to the power K. So for Bernstein-Vazirani, we have a function such that F0, or I should say F inverse 0 and F inverse 1. So this is all the elements which are mapped to 0, and these are all elements which are mapped to F inverse 1. They have the same size, and actually one of them is the subgroup and other is the coset. So in that case, so now we can give kind of a characterization of these biggest groups. It is decided by some A such that is equal to 0, where X is element of G. Remember, this is mod 2. We have seen this as an exercise in our course. You can try to show that this set or I should say you already see connection with what we have done before. We have seen Bernstein-Vazirani algorithm, and we already see that our function divides the group into subgroup and a coset. And this division is going to be very, very helpful going further. I would just say, in general, given any subset of G, we will always remember cardinality of H divides cardinality of G, and more importantly, G can be partitioned into these many cosets of H. So this property which you saw here, that you have a subgroup and you have coset, all the sets are distinct to each other and they partition G, this actually remains true for any general subgroup. You pick any general subgroup of G, cardinality of H will divide cardinality of G, and whatever be that number, there will be that many cosets so that G can be partitioned into these many cosets of H. And just to make a picture, so this is your entire group G, and it is divided into these many parts. Each of the part is a coset. That means it can be written as some element of the group plus H. Each of the elements are distinct here and they cover n times of G. This structure is very, very useful. And this holds true for whatever be the group, whatever be the subgroup. And again, as an exercise, you can find out what are the cosets of this simplest non-trivial subgroup of Z to the power k. In Z to the power k. And you will see that they exactly match with pairs of Simon's problem where they have the same color. Again, the subgroups and cosets of Z to the power k have a deep relevance to the algorithms we have discussed before. So you find these cosets and connect them to Simon's problem discussed. Let me just remind you what the Simon's problem was. There was a hidden string in Z to the power k such that X and X XOR S has the same color. So sorry. This is your Z2 cube, and let's say your S is any favorite S, which is not 0. Let's pick it as 101. So in that case, these have the same color, and then these will have the same color, and so this was the Simon's problem, and this exercise is to relate this coloring with the cosets of Z to the power k. So after giving this background, I think we can move to Fourier analysis, but I just want to make a comment that whatever groups we have seen, they are all abelian. Z2, Zn, Z2 to the power k, if you talk about integers, complex reals, all these groups are abelian in the sense that G1 plus G2 is always equal to G2 plus G1.
It might be useful to note that the cosets are themselves isomorphic to a group.
Oh, yeah, so I understand that you are saying that if I think of these itself as elements, cardinality of G by cardinality of H, they form a group in itself. But we don't use that in quantum that much. So that is true, but we won't be covering that here. The coset group, we won't go into detail of. Yes. So there is a lot of nice structure, and I encourage you to look at group theory and find out what we can say about the groups. This has very, very nice structure which you already see here, and read more about it and have fun. But, this is what you need to definitely know to remember. Great. So these are called Abelian or commutative group. So we will now remember for the future discussion that our groups are Abelian from now on. Okay. Okay. By taking example of Bernstein, Vazirani and Simons, we saw that we want to analyze functions of this kind. Or to be precise, in general, we are interested in analyzing functions which look like going from a group to some numbers. Again, for Bernstein, Vazirani, this simply here we had 0, 1. For Simons, this would be some finite set, which was simple, but in generality, we are interested in analyzing such functions. Where G is finite and Abelian. This is what we want to do in the remainder of the lecture. We want to analyze functions which go from group to numbers where the group is finite and Abelian. So my first question is, what should be the representation of this function? Or other way to say it is, I have a function in mind which takes these groups elements and maps them to some complex numbers. How should I present this function to you? In what way can I give this function to you, specify this function to you? And this is not that difficult. If I say that, let's look at all my elements of G, they are finite. Let's write them as G1 to Gn. Then one of the simplest representation of this function is that I say, what is the value on G1? So this is f of G1. This is f of Gn. So I have given my function as a vector to you, where the length of the vector is the cardinality of G. Okay, and I can keep my functions like this, analyze addition of functions and things like that. I can try to do linear algebra over F, because I can add functions, I can do various things, I can multiply them by constants. But if you notice here, what should be the representation of a function, or the, let's say, indicator function of an element of the group? You would say, sure, 1 0 0 0. Okay, Gi. Place, they form a basis. This is the standard basis for these elements of the group itself. So this is great, this is a good representation, but the only problem with this is not keeping the structure of the group, right? We have imposed a linear algebraic structure on our group, we have assigned them vectors, but these vectors are no way related in terms of the group structure. What I mean to say is that if there is a group property, for example, G1 plus G2 equal to G3, this is really not reflected in this representation, right? So the question is, can we have a representation which respects the properties of the group. Right? And this gives rise to the idea of